Welcome back, everyone. In this video, we will take a close look at one of the most promising new technologies in global space communications. Germany is taking a lead role in developing laser communication satellites that are set to change how data moves in orbit and between Earth and space. These satellites are not just test models, but part of real networks being deployed in Europe and beyond. By learning how they function and what advantages they bring over traditional radio systems, we can better understand what to expect in the near future. Please subscribe now. To begin with, we should understand why satellites need faster data links at all. Traditional radio communication has served space missions for decades. It works by sending electromagnetic waves at radio frequencies through antennas to ground stations or between satellites. However, radio frequencies are limited in bandwidth and face growing congestion as more satellites are launched. This congestion makes it harder to guarantee high data rates and low latency. Laser communication offers a way to move past those limits by transmitting information with light rather than radio waves. Laser communication satellites rely on highly focused beams of light in the near-infrared range. These beams can carry far more information than radio signals because the wavelength is much shorter. A single laser link can transfer data at rates measured in gigabits per second compared to tens or hundreds of megabits typical of advanced radio systems. In practical terms, this means that satellites with laser terminals can pass on entire sets of high-resolution images or scientific data in minutes rather than hours. For Earth observation or security uses, that speed is decisive. Germany has positioned itself as one of the leaders in this technology through companies such as Tesat-Spacecom. Tesat has already flown laser communication terminals on several European satellites and even on missions with the European Space Agency. Their terminals have achieved multi-gigabit-per-second links between satellites separated by thousands of kilometers. The company emphasizes the reliability of these terminals in space conditions, including thermal changes and vibration. By scaling production, Germany aims to make laser communication a standard part of future satellite constellations. One of the main advantages of laser links is that they're very hard to intercept or jam. The beam is so narrow that, unless a receiver is directly in line, it just won't detect the signal. This gives both commercial and government users much higher confidence in the security of their data. Radio systems, on the other hand, can be interfered with by anyone transmitting on similar frequencies. With lasers, the level of precision required to disrupt a link is so high that it's considered extremely unlikely. This makes laser satellites attractive for defense and secure government communication. Bandwidth is another crucial point. A radio frequency system might use channels of a few tens of megahertz, while a laser system can exploit channels in the terahertz range. The increase in available spectrum directly translates into higher throughput. To illustrate the difference, one can imagine a single laser satellite transmitting more data in 1 hour than a whole fleet of radio-based satellites of similar size. This efficiency reduces the cost per bit of transmission and enables services that were previously impractical, such as real-time cloud storage from orbit. The comparison between latency in radio and laser communication also favors lasers. Latency is the delay between sending and receiving data. Since both radio and light travel at the same speed in a vacuum, the key factor is the ability to encode and decode information quickly. Laser terminals use advanced modulation methods that reduce overhead and increase speed. In intersatellite networks where data must hop across several nodes, the cumulative latency savings can be significant. This could allow near real-time relay of sensor data from one part of the globe to another. The way modulation works in optical systems is actually different from radio. In radio communication, phase and amplitude are often varied across a carrier frequency. But in optical systems, engineers can use intensity modulation, phase modulation, or even polarization modulation of the laser beam. These techniques allow multiple data channels to be encoded on the same light stream, which boosts throughput. Error correction coding is also more efficient in optical systems since the narrower beam reduces interference. The result is a higher quality signal with fewer retransmissions, which further improves latency and reliability. Encoding methods in laser links are highly advanced. Quadrature amplitude modulation and pulse position modulation are commonly used, but recent research explores multi-level coding where several bits are represented by each pulse of light. This allows gigabits of data to be carried per second, even with compact terminals. German engineers have focused on creating systems that can adapt their encoding in real time depending on link quality, much like adaptive streaming on the internet. When atmospheric conditions or pointing errors reduce link clarity, the terminal can automatically switch to a more robust code. Ground stations introduce their own challenges. When a laser beam passes through Earth's atmosphere, it is distorted by turbulence. To overcome this, adaptive optics are used. These systems rely on deformable mirrors that can change shape thousands of times per second, correcting for the atmospheric distortion. Wavefront sensors detect how the light is being bent and provide feedback to the mirror. German and European ground stations equipped with adaptive optics can recover a signal that would otherwise be scattered, making optical downlinks feasible even under non-ideal conditions. Tesat-Spacecom has partnered with international players including Airbus Defence and Space to expand adoption. Their terminals are being integrated into European data relay system satellites, which act as high-speed data routers in space. This system allows Earth observation satellites to send data immediately, without waiting to pass over a ground station. The European Commission promotes this as a way to improve disaster response and security monitoring. By having the information within minutes rather than hours, decision-makers gain a clear advantage in time-sensitive situations. Another case study involves Tesat's work with international broadband constellations. German hardware is already proving itself in commercial markets, with satellite operators worldwide selecting Tesat terminals for cross-link capability. The growing number of buyers demonstrates that this technology has moved beyond demonstration into widespread use. It also highlights how Europe can compete effectively in a sector often dominated by manufacturers in Asia and the United States. From a technical perspective, aligning two satellites to create a stable laser link is not trivial. The pointing accuracy must be within a few microradians, meaning the system has to keep the beam locked on target despite the movement of spacecraft in orbit. Tesat developed fine steering mirrors and closed-loop tracking systems that achieve this precision. The terminals also use beacon lasers to help acquire the link before switching to the high data beam. These innovations are critical because even a slight misalignment could break the connection. Thermal management is another design challenge. Laser diodes generate heat, and in space there is no air to carry it away. Engineers rely on heat pipes and radiators to move thermal energy away from sensitive components. Tesat terminals have shown that they can operate for years without degradation thanks to careful thermal design. This contrasts with earlier prototypes from other firms that suffered from overheating or limited lifetimes. The reliability of German hardware is one of the reasons it has been selected for European flagship missions. Looking ahead to 2026, one can expect a significant increase in the number of satellites equipped with laser terminals. Several European constellations for broadband and Earth observation are scheduled to include them as standard equipment. This will expand the data relay capacity available to European governments and commercial operators. Predictions suggest that by 2026, more than 100 active laser terminals could be operating in orbit from European satellites alone. This marks the point at which laser communication shifts from experimental to mainstream. By 2027, adoption is expected to spread across multiple orbital shells. Medium Earth orbit constellations may use optical links to connect navigation satellites, improving the resilience and accuracy of positioning systems. Low Earth orbit constellations will increasingly rely on laser crosslinks to route traffic directly in space, rather than through congested ground stations. Analysts expect at least 5 major satellite operators to deploy large constellations with optical terminals by 2027, putting thousands of units into service. Germany will benefit directly as a supplier of this hardware. By the late 2020s, we may also see integration of laser links into interplanetary missions. The European Space Agency has already discussed the possibility of using optical links for Mars orbiters. While the current focus is on Earth orbit, the long-term benefits of optical communication for deep space are enormous. A single optical terminal could deliver the same data rate from Mars that currently requires very large radio antennas on Earth. Germany's early work in this field positions it as a key supplier if such missions move forward. Medium-term implications include the formation of true satellite data backbones in space. With laser crosslinks, satellites no longer need to send all their data directly to the ground. Instead, they can pass it through a network of peers until it reaches an available ground station. This model mirrors how the internet functions on Earth, with routers and switching points. Germany's role in providing the hardware for these space-based networks places it in a strategically important position for the global data economy. There are challenges to address as well. One issue is the standardization of protocols. Different companies have built laser terminals that do not always interoperate. The European Space Agency is working with Tesat and others to develop common standards so that satellites from different manufacturers can talk to each other. Another challenge is cost. Although prices have fallen, each terminal still represents a significant investment. Mass production will help, but there is a balance to be found between performance and affordability. Alright, so another consideration is regulatory. Because laser communication beams are so narrow, they don't interfere with existing radio spectrum allocations. However, international guidelines still need to be created for safe use. The International Telecommunication Union has begun discussing frameworks for optical communication. Germany's leadership in this field ensures that European interests are represented in these discussions. By shaping the rules early, Europe can avoid the bottlenecks that have hindered radio spectrum management. From a competitive standpoint, Germany faces rivals in Japan and South Korea, which are also developing advanced optical communication. However, the maturity of German hardware gives it a clear head start. If current trends hold, German terminals will be flying on hundreds of satellites before many competitors leave the prototype stage. This provides both revenue and influence in how the global market evolves. It also ensures that Germany remains an indispensable partner in multinational satellite projects. Looking further ahead into the early 2030s, experts expect laser communication to become the default for all new satellite platforms, regardless of mission type. Earth observation, navigation, and broadband constellations will integrate optical terminals as standard equipment, and even small CubeSats may carry miniaturized versions. As prices fall and protocols become standardized, optical networks could span not only Earth orbit, but also extend to lunar gateways and Mars missions. For Germany, this means continued growth of its aerospace sector and a sustained role in shaping the global communications infrastructure of the next decade. For viewers, the key takeaway is that laser communication satellites are not science fiction or distant promises. They are already operating today, and by 2026, they will be part of everyday satellite operations. This means faster internet from orbit, more timely weather and disaster monitoring, and more secure communication for governments. Germany has quietly built a strong industrial base in this area, and its role will only grow in the coming years. Thank you very much for watching. Please like and subscribe.